basically I had assigned you work. Previous to that, what we were working on. Anyone can tell me quickly. By that time, I'll just present the slide. What was the topic what we were dealing with?
We discussed about earlier developments on Bingham plastic and
Okay.
static and dynamic shear stress response.
Okay, okay. Is the slide visible to you all?
Yes, ma'am.
Okay. So basically in previous class we were dealing about some mathematical models related to Bingham plastic and related models. So these are all the sections what you have to understand under the mechanism and properties of shape memory ER fluids. So we started with mechanism and properties of ER and MR fluids. We did with basic models of macroscale fluid mechanics with the sections of fluid composition and behavior. So we have done with fluid composition and behavior. We done with discovery and early developments. Later we came into the picture of developing the mathematical model for Bingham plastic and related models. So we have completed until the Bingham's model in the last class, right? So how to determine the pre-stress and the post-stress, the yield strength, how does it vary? So all these aspects we dealt about in the previous class, like how the initial shear stress will be there, that will be more than that of our yield stress, so how it will come back. So all those things we analyzed with the relation of shear stress to shear strain responses for both static and dynamic shear stress. So this was about the mathematical modeling equation related to Bingham plastic and related models. So next model what we have to go is related to the pre-yield response, and we have the post-yield response. So we dealt about this pre-yield and post-yield related to Bingham's plastic model. So now we are going in depth related to these yield responses. So first thing you have to go up now with pre-yield response. So what happens basically in the pre-yield response, you have to check. So basically before starting you can see that you have a graph which is a typical shear stress to strain graph. So here we have plotted the shear stress values and here the strain values has been plotted. So this could be either for ER fluid or for MR fluid, right? So the shear stress depends upon the force what you are applying or the load what you are applying. So subjecting to the force F3, the shear stress what you get is written over here. So subjecting to the force F2, the shear stress what you get is being mentioned here. Okay, so again the shear stress subjected to the force F1 what you are getting is mentioned over here. But if you draw a line intercept towards your y-axis, then the stress, shear stress, what you get will be nothing but your yield stress. So if tau suffix y is written, then that is the yield stress. The ultimate stress, what you are getting, will be shown over here. But yield stress will not be the pre-stress. That is the ultimate stress what you can get, right? So initial stress what it was without subjection of the load. So that is the pre-yields. And after the subjection of the load, what is the amount of stress retained? So that will be given in our post-yield. So this is the higher limit at which the stress and the strain gradually increases rapidly. Okay, so this is the ultimate point where it has the maximum shear stress. So once from there it starts reducing even after the stress applied is more due to subjection of load, the strain remains consistent. So at that stage, the amount of yield stress retained in the given object is termed to be as the post yield. So now we have to go with respect to the pre-yield, understand that in depth, as well as the post-yield also. It could be either related to ER fluid or related to the MR fluid. So this is what you have to learn basically. So now I will get back to the slide here again. So here, before starting, you can see according to Bingham plastic model, the stress will be less than the yield stress. So yield stress, I told you the maximum stress. So the regular stress will be usually less than the yield stress. And the yield stress is represented by tau suffix y. Okay, so the normal stress what you have, which is lesser than the yield stress, will not produce any flow in the ER or MR fluid. Why? When you subject some force for the fluid, then only the fluid will flow, right? So if there is no external force applied, then there will be no flow of the fluid. So due to no flow of the fluid, the amount of shear stress which is coming across the fixed and the movable plate will be very less. Since the shear stress is lesser than that of the yield stress, we can assume that where the stress is less, at that condition, there will be no flow with respect to either electrical rheological fluid, yeah, magnetic rheological fluid. Okay, so but in reality, it has been assumed that the fluid naturally responds to the stress in this range. In reality, this has been assumed, but in actual, if we go with respect to the mathematical equations, right, the theoretical approach says that there is no flow in either ER or MR fluid. But wherein in actual, in practice, when you perform some test, it has been told in reality, in actual, the fluid will respond to the minimum amount of stress subjected. Because when the fluid is held in stationary also, a slight movement of the moving plate due to external atmosphere can also create a small amount of stress. So the small amount of stress can make the fluids flow in a very slow rate. So that is what being told. In reality, it might show some movement, and hence it has been told it responds to even some minor amount of the stress. Okay. So this is a concept what we have to understand. So first you should know what is pre-yield and post-yield. So this is the point at which the shear stress is ultimate. So the values before the ultimate value is the pre-yield, and the values what you get after this ultimate value of stress is the post-yield. So in post-yield, always you should see that the shear strain will be consistent. Even though the shear stress increases, there will be a constant steadiness in the shear strain. So that is associated with respect to our post yield. Okay, so we can also call this point as a saturation point. So the point until which, so where if you have a fluid, suppose you have a fluid and a top plate and a bottom plate, the top plate is moving and the bottom plate is held stationary. So due to the movement at the top plate and the movement and no movement in the bottom plate, the shear stress comes into picture. So due to the shear stress, gradually shear stress will increase, and as a result the shear strain also increases. So it increases rapidly. So at particular time it gets saturated, and that is the maximum shear stress it can be induced in the given fluid. So once that point is crossed, thereafter the shear stress gradually reduces and it remains consistent enough with respect to the strain induced in the body. So at that point, if you draw an intercept to the y-axis, so this value is called as our yield stress. So the shear stress value will be usually higher than that of the yield stress value at the ultimate point. So the values of the shear stress before this ultimate point is called as a pre-yield, and the values after this point is called as a post-yield. So with that clarification, you should now proceed further. So it is also told that for many purposes, it might be regarded as viscoelastic solid. Okay, so here the ER or MR fluid, you know, it is not a solid material. But since it has been told in reality, the fluid naturally responds to the amount of stress in the range. In many purpose, it is also regarded as viscoelastic solid, what they are terming. So viscoelastic material is such a thing that it can be compressed and it can come back to its original position. Okay, so they're comparing that related to the viscoelastic material. But in typically, we usually call that as an ER or MR fluid only. We don't correlate to viscoelastic solid. but in some purposes it can be regarded as viscoelastic solid, is the thing which has been mentioned. Okay. So the graph we have explained already. So the graph typically shows the stress strain characteristics along with the pre-yield as well as the post-yield for ER and MR fluid. So when it is loaded with respect to the load bearing capacity, so there will be an ultimate load what it can bear, so that could be called as an yield point until which it can bear. So you have to identify which is the yield point for the given ER or MR fluid. So basically based on that you will calculate the other values, the post yield and the pre yield values. Okay, so later you have to see that, yeah, this graph I have explained already, the same thing has been mentioned. So this nature of pre-yield response was then explained by an person in a journal article in 1994. So there were three researchers, Wiss, Carlson and Nixon, right? So these three together just developed and some research correlations, and they suggested that the one set of non-linearity in the storage module defined below is an accurate indicator. Okay, so just first understand what you mean by pre-yield response. So once you have understood, you have to explain the diagram here basically. So after explaining the diagram, you just tell that to get more clarity about how the yield strain will correspond to its particular stress, a curve was been analyzed. Okay, and this curve was been analyzed and put in practice with actual definition by some materials, but it was not so clear enough, because the graph we can easily understand, but it is when it is applicable to some material basically, then it has to show as per the theoretical explanation given for pre-yield response, but it was not clear enough. And as a result, since it was not clear enough, what they did is a researcher in 1994 suggested one concept related to accurate indicator of the yield. Okay, so which is the accurate indicator to identify where the yield point is. Okay, because we can tell that this is the yield point, but when it is subjected to a particular ER fluid, yeah, MR fluid, how will you identify that this is the yield point of that particular fluid? So you should be having some indicator which helps in identifying the accurate value. So they suggested that they should develop an accurate indicator to identify the yield point, and it should also correlate with respect to the yield stress value, and the yield stress value will not be like an dynamic one, it will be static. So that is the upper limit, the yield stress value what a material can bear. It cannot be movable or it will not fluctuate, because once the yield point is crossed, so it slightly gets reduced and later it will be consistent towards. So at that point of consistency, if you draw a intercept, you will get the yield stress. And this is called as a static yield stress, which will be constant throughout. Okay. So they tell that they need a particular accurate indicator to identify the yield point and also to correlate with respect to the static yield stress. So this is very much essential what they suggested. So these people focused on pre-yield response only. In this graph, we have two parts. One is a pre-yield, another one is a post-yield. So these research fellows focused on only the pre-yield part. So they told that we need a particular indicator which indicates this ultimate yield point. And after indicating the yield point, it should correlate with respect to the yield stress what it is getting. Okay, so if you have a proper correlation between the yield point and the yield stress, then you can identify and tell for which material which will be the yield point and which will be the pre-yield value for it. Okay, so these values have to be determined. So this amount of suggestions were given by Wiss, Carlson and Nixon in the year 1994. So based on their concepts, here they claimed that the shear stiffness of viscoelastic solids, they are using the word viscoelastic solids because the condition of evaluation of the yield stress in ER or MR fluid was compared to be similar to that of the viscoelastic solid nature. Since they told that the purpose may be regarded as viscoelastic solid, so this concept was taken by Mr. Wiss, Carson and Nixon, and they told that the shear stiffness of viscoelastic solids will include unyielded ER and MR fluid. So what do you mean by it? Now they are comparing the ER and MR fluid with respect to viscoelastic solids because the nature of analysis of the yield stress in case of smart fluids, they are telling that it is similar to that of the viscoelastic solid nature. So, if they compare the ER fluids with viscoelastic solid nature, then they should justify that what about the shear stiffness in case of viscoelastic solids. For that purpose, they informed that the shear stiffness in case of viscoelastic solids will include the unyielded value. So if you go back to the graph here, it has the shear stress value, right? Which is a yield stress, and it has a pre-yield and the post-yield value. But apart from these, there will be some values which will be associated to unyielded ER and MR values. Why? Because this provides a yielded value, means the yielded value for the given ER or MR fluid. So you can measure the yield stress here. Apart from that, you know the pre-yield value and the post-yield value. But as it gradually increases from zero when the stress and the strain increases proportionally, so there will be some variation in the stress here which has been induced, and that is not been considered at all. So those are non-yielded stress values. So this shear stiffness of viscoelastic solids claimed that this includes the unyielded ER and MR fluids, and this unyielded MR and ER fluid is represented by the complex shear module, and here G is called as a storage module. So if you come across the letter G, you should refer to be as a storage module, right? So here G dash is called as the storage module, and it measures the material ability to elastically store strain energy. We are speaking about the storage module because we are comparing ER and MR fluid with viscoelastic solids. So when viscoelastic solid comes, it is associated with shear stiffness rather than yield stress. Okay, and as a result, if when we speak about the shear stiffness, we should also assume the stresses which are not yielded. So they assume that this shear stiffness of viscoelastic solids will include the unyielded ER and MR fluids. And this is represented by complex shear modulus equation. So this is given by G star is equal to G dash plus. Okay, so you have a complex number J terms of G double dash. So here G dash is called as the storage module. Okay, and this storage module will measure the ability of the material to store the strain in elastic nature. The material could be compressed. Since it is viscoelastic solid, it could compress and again expand. So when you have a viscoelastic foam and you apply a load on it, then it gets compressed. So once the load is removed, it can come back to original position because it has elasticity nature in it. So when it has compressed and come back, so even at that elastic nature, it can store some amount of strain in it due to the applied load. So they tell that G dash is nothing but the storage module, and this storage module will help to measure the ability of the material to store the strain at elastic condition. So this is referred to be as G dash. Similarly, we have one more part in the equation, which is G double dash. So G double dash is termed to be as a loss modulus, and it is associated with the dissipation of energy during the deformation. Why? Because suppose if you consider this as an viscoelastic foam, and when you apply pressure on it, so this gets compressed. right? After compressing, it will come back to original position. Due to its elastic nature, it comes back to original position. So at that position, it will store some amount of energy, which is called as our G dash. But during this compression and expansion and storing of strain energy, there will be some amount of loss of energy, which is called as dissipation energy. So this happens due to deformation of the given object. So viscoelastic solid can compress and come back until certain range of loaded values. If it is heavily loaded, then the material might get deformed. So when it is deformed, there will be some loss of energy. So this dissipated energy is termed to be as the loss modulus. So complex shear modulus will be the combination of the amount of stored strain energy in elastic condition plus the amount of energy dissipated during deformation, where J is a complex number. Okay, because we are evaluating complex shear modulus, we have to refer I, J, K terminologies related to complex numbers, right? Since it is a second terminal, the complex number what we get here is J. If you were supposed to use complex number in the first terminal, then you have to use it as I, J and K. All those you know it. Since we are relating the dissipation of energy and hence we are using the complex variable here, which is nothing but as J. So from here onwards, if the equation for complex shear modulus is being asked, it should be G dash is equal to G, it should be G star is equal to G dash plus J times of G double dash, where G dash is the storage module and G double dash is a loss module, which is associated with the dissipation of energy during the deformation. So if you want to calculate what is the loss factor in the storage module, then you have to take the ratio of G double dash to G dash. So if you take the ratio of the loss modulus to that of the storage modulus, then you'll come to know what is the loss factor associated it with. Okay, so this is about how to calculate the loss factor for pre-yield response when we compare ER and MR fluid as an viscoelastic solid. Okay, so when we assume that, we consider that even the unyielded stresses comes into picture in case of ER and MR. So based on that concept, you will be having one real part and one imaginary part. So real part is the G dash, which is called as a storage modulus, and the imaginary part is our G double dash, which is the loss modulus associated with the dissipation of energy at deformation. So if you want to determine the loss factor, then this is the equation what we use, G double dash to G dash. So it was identified by Wills in 1994. We are explaining the same paper which was been declared by these researchers in 1994. So in 1994, they determined that they told that it can be determined by measuring the phase difference between a strain wave input to a material. So what does it mean here? The loss factor, which was shown as G double dash to G dash, they disclosed that this loss factor can be evaluated, okay, by the stress wave. So that was been told in 1994. How they determined it by measuring the phase difference between strain wave input to an material. What is the change in phase? It comes into picture when you go with ER fluid or MR fluid. When you are subjecting it to high temperature or high pressure, the viscosity of this fluid changes at different phase. So they will measure the phase difference which comes into picture related to the strain variation. So based on the strain variation, there will be change in the phase. So based on the phase differences, they will evaluate the obtained stress wave. So from the stress wave, you can evaluate what is the loss factor, because it will be having the useful part which is G dash and also the waste part which is G double dash, which is associated with the dissipation of energy. So this helps in determining the loss factor basically for either ER or MR fluid. And it was told that predominantly elastic material, so all the elastic material here, either ER or MR fluid, will exhibit a very small phase difference and a very small loss factor, typically less than 1. So I didn't. So they told that this is a method to evaluate the loss factor. How they evaluate it? They will get the result in the form of stress wave. To get the result in the form of stress wave, what they have to do? They have to measure the phase difference which is occurring between a given strain wave input to a material. So when you apply a load to the material, what is the amount of strain induced in the body? So based on the effect of the strain and wave input will be displayed, right? So this will help to evaluate the loss factor associated with it. And it is also told that this loss factor will not be very high. It will be negligible, which is less than zero point 0.1 value. Why? Because the phase difference what you get will be comparatively very small. Due to comparatively very small phase difference, the amount of loss factor associated with that also will be very less. So this is a thing which has been explained with respect to our viscoelastic material. And also it is told that in a viscous material, the phase difference will approach 90 degree and the corresponding loss factor will be quite large. Again, it depends upon how viscous your material is. Because in ER fluid, you will subject electrical field into it such that it helps in enhancing the viscous nature of that fluid. Similarly, in MR fluid, you will subject magnetic field so that it helps in enhancing the viscosity of that fluid. So when the viscosity is high, it resembles the nature of viscoelastic solid, and hence it is compared with viscoelastic solid as told before here. Okay, so in that condition, when it is totally a highly viscous material, they tell that the phase difference will be approaching 90 degree. So there will be an huge phase difference in a viscous material. So at that case, the amount of loss factor which has been obtained will be quite large. So you should understand when the loss factor will be high, when the loss factor will be low. So the loss factor will be comparatively higher when the phase difference is higher. Okay, so when the phase difference is low, then the loss factor will be low. So this is what you have to understand. Any doubts until here? Hello?
No.
So this is about the pre-yield stress. So if they ask you to describe the pre-yield stress, you have to tell that as per the Bingham plastic model, the stress what you get will be less than that of the yield stress. It could be either for ER or MR fluid, but for many cases it is compared with respect to viscoelastic solid, because when you subject the electrical field or magnetic field, the viscosity of the fluid increases. It acts as a semi-solid kind of thing, and hence you are assuming that to be as viscoelastic solid. Later you will explain the graph, which is the ultimate yield point, which is the pre-yield and the post-yield, and how you evaluate the yield stress values. So that you will explain with respect to the graph. Okay, and then you tell that to analyze this peak stress, yield stress, and the pre-yield responses, there was no clear definitions as such, and hence in the year 1994, Wiss, Carlson and Nixon developed some model associated to evaluate the static yield stress. And they told that to measure this yield stress, we need an accurate indicator. So if you have an accurate indicator, they can indicate what is the yield stress value, what is the ultimate yield value, and also they can correlate with the yield stress values. So this is what they claimed. So based on the assumption, then they derived a small equation for complex shear module. So they told that when you assume the ER or MR fluid to be as a viscoelastic solid, it will be having unyielded stress also. So this unyielded stress will be represented by complex shear modulus. So this complex shear modulus is given by G star is equal to G dash plus J into G double dash. So it is a complex shear module where you'll be having a real part and an imaginary part. So the real part consists of the storage module. So where you store the amount of strain which is being delivered at the elastic condition of the material. So this was an useful part. And apart from that, there will be some dissipation of the energy, what you represent as G dash. So the ratio of these two will provide the loss factor. And they told the instrument how you can develop the loss factor by measuring the phase difference between the strain wave, what you get based on the input what you are giving. But still, even though they told what is the procedure to determine the loss factor, they claim that the amount of loss factor what you get in any ER or MR fluid will be comparatively less than zero point 0.1. Why? The phase difference will be very small and the loss factor also will be very small. So this was the thing what they approached. Okay, but if it is a viscous material, suppose if you use ER and MR fluid with high viscous value, so then what happens that the difference reaches 90 degree, the phase difference will reach 90 degree, and hence at that case the loss factor will be comparatively higher. So this was a thing which was clarified related to the pre-yield. So later you have the last part of the mathematical model. So we studied with two mathematical models. One is the Bingham and plastic model. The second one is the pre-yield response, in which we dealt about the complex shear modulus, which includes the storage module and the energy dissipation one. And thirdly, you should understand the post-yield flow and device geometry. So this is a bigger one which has a derivation as well. So we'll see like how much we can cover, we will do it. So you know like what is pre-yield and post-yield. So we focused until now related to the pre-yield part. So now it's time to go up with the post-yield. So once the yield point has crossed, I told that the yield stress will reduce gradually and it become consistent towards. So this value which is consistent throughout will be towards our post-yield value. So we have to understand what is this post-yield flow, right? So here what you have to understand is if you have any devices made up of ER or MR fluid, okay, so what happens is at any time a small portion of the fluid might be subjected or applied to electrical or magnetic field. Obviously when you make a smart device using smart fluid, you have to apply either the electric field or magnetic field, but you are applying a part of electric field or magnetic field to some portion of the fluid, right? So it could be for the surface of the smart fluid, or it could be across the surface of the plate what you have, the top plate and the bottom plate, but you will be applying for small area, a small portion, so that you should know. So without applying the electric or magnetic field, your MR or ER fluid will not work basically, and hence we apply a small portion of the electric or magnetic field to that of the ER or MR fluid, but it is applied to a particular area, not throughout, and the remaining part will be free to flow as conventional low viscosity fluid. So what you have to understand here is you have an fluid film which is moving from this end to this end. Above this you have a top layer and bottom layer. So now you are subjecting the electric field, considering that it is an ER fluid. So when you subject an electric field, it is told that you will subject this electric field for some small area. Suppose if you have the fluid from here to here, suppose from 0 to 10 centimeter, you are applying the electric field from 0 to 4 centimeter only. So in this position, it remains as a smart fluid, right? Because the viscosity also will be high in this position, it has become a smart fluid due to subjection of electrical field. So viscosity will increase and it results in the formation of the fibrils with required gaps. Okay, so then that is a function what we basically need. But the remaining part of the fluid, which is not subjected to the electric field, will flow normally in a conventional way, how it was. And here the viscosity doesn't change. So it will be having a low viscosity and it will flow as per its type of fluid condition without any external effect. So remaining fluid will be free to flow, but whereas the part of the fluid associated with the electrical field will behave in a different way. Means it behaves like an ER fluid due to the ER effect. So this you have to understand. So it is not like you're applying the field for throughout the material, only for a particular section. So that section will be having high viscous and the remaining liquid flows in a conventional way. Okay, so this one concept you have to understand. The second concept is usually the field is created across a small gap whose surface serve as both electrodes. You know that gaps will be created usually. Why gaps are created? If this is your fluid and it has a top plate and a bottom plate. So when you apply the electrical field, what happens is the particles what you have in case of electrical fluid we use some particles which can act as a conductive media, right? So those particles gets charged, so positive and negative ion get attracted and it results in the formation of fibrils or structure 1, structure 2 and structure 3. But these structures will be placed with respect to some gaps in between. Okay, and hence this is the same thing is been told. So when you apply the field it results in formation of small gaps. Okay, and these gaps will serve both as an electrode or pole pieces. So these gaps will serve as an electrode if it is an ER fluid. If it is an MR fluid, then this gap will serve as the pole pieces. In magnetic MR fluid, you need the north pole and the south pole. But whereas in case of ER fluid, you need the electrodes as a conductive media, right? So this gap will behave like an electrodes in case of ER fluid and it behaves like the pole pieces in case of MR fluid. So this happens as the wall of a change confined towards the fluid. What do you mean by wall? So you'll be having a top plate and a bottom plate, and in between you'll be having the fluid layer, right? So when you subject the electrical load into it, electrical field into it, it results in formation of fibrils with some gaps. So these gaps will work as an electrodes, and this will happen when the walls are confined towards the fluid. So this is the wall of the top plate and this is the wall of the bottom plate. So the top plate will be moving and the bottom plate will be fixed. So the wall will be confined towards the layer of the fluid which is nearer to the top plate. So these are the concepts what one has to understand before going for the derivation. Okay, so this is the thing. So after understanding and next assumption what has been done is for the analysis purpose, these walls are often modeled as parallel and flat plates. So to analyze the effect of this, the plates what we have at the top and the bottom are assumed to be flat plates. And also it is considered that both the plates at the top and the bottom are parallel to each other. It is not like one plate inclined to one end and another plate is horizontal. You can't use that way. Both the plates should be flat and both the plates should be parallel. Okay, so these are the things what one has to keep in mind. So one thing is when it comes to any ER or MR fluid, it has to be subjected for either electrical or magnetic field. So the area in which the electric field is applied, that only behaves with high viscous nature and the remaining fluid will flow in a conventional way. So that is the second concept what you have to understand. The third one is when you subject an electrical or magnetic field, it results in the formation of fibrils or the structures with some gap in between. Okay, and this gap will be proportional. Okay, so this will act as an electrode. This gap will act as an electrode or the pole pieces. and this behavior will vary with respect to how good the fluid is confined to the top surface of the plate. Okay, so this is about the nature how the fluid will behave like an electrode or the pole pieces subjection to the external field. But in analysis purpose, we have also assumed that the top plate and the bottom plate will be parallel and both the surface will be flat. So these are the assumptions. So based on the assumptions, some resulting equations were being formulated. Okay, so they told that the resulting equations are applied frequently to annular or other non-flat geometries with acceptable results. So this what we gave the assumption was for flat plates, and later they told that even it could provide a good results for even non-flat geometries also. The amount of results obtained was acceptable, what they are telling. So for the analysis purpose, you can assume that the model is exactly parallel and with flat surface, and you can also assume that the model is parallel with some non-uniformity in the plate surface also. So both could be acceptable what they are claiming. These are all theoretical assumptions and theoretical models. So in order to analyze this type of models, there are some realistic models are also available, what they claim in the research paper. And they have given an example as cylindrical dampers. So cylindrical dampers are one realistic model explanation what one has given in the research paper, right? So this is about the basic concepts what you have to understand related to the post yield flow and the device geometry. Okay, so you can see the diagram over here. So this is the ER or the MR fluid, and you will be having a top plate and a bottom plate. Okay, so what happens here basically, you can compare this with respect to fixed plate and the moving plate. So this is a fixed plate condition in which both the plates will be fixed, but whereas in sliding plate, both the plates could be slided. So when it is in sliding, then the shear stress comes into picture. With what velocity it is been sliding, also that will be given. So this is the length of the plate as well as the length of the fluid in which it is moving, right? And this is the height of the fluid films, mean to say this is the thickness of the fluid film, and this is the width of the fluid film. So based on the apply, you will apply the pressure. So this pressure will make the ER or MR fluid to move. So it could be an electrical field or it could be an magnetic field. So based on the fluid you are selected, you will subject it to the external force, right? So this is about the structure, how it looks at stationary as well as sliding. So here I told pressure, here force cannot be applied because it is a fixed plate. Since you are storing some potential ER fluid between the two plates, obviously some pressure will be there. I told that even when there is no loading, some amount of stress on the strain which has been induced in the body is measurable as per one of the researchers. And later you apply force on the top plate because the top plate is moving. So when this top plate is moving, what happens is it gets sheared enough. So see, due to shearing, the yield, you will get shear yield stress and the strain. So again, the thickness of the fluid, everything will remain the same. So you will identify the gap geometries and the fluid shear modes. So you have the gap geometry here. So like this is a top plate and the bottom plate. So when you apply the force, due to the shear, the viscosity also increases, and due to this you will be having the fibrils formed, and in between the fibrils you will be having some gap. Suppose if this is the first fibril and this is the second fibril, in between you will be having the formation of gap. So this is called nothing but the gap geometry. Okay, so what I explained is now being shown here in the diagram. So with this information, we can proceed further. I'll just complete this slide and later the derivation could be taken in the next class. So the graph will show the nature of the ER and MR fluid when it is subjected to the force, provided one plate is movable and one plate is fixed. So here it has been shown that the shear may be produced in the fluid. So how it can be produced? Either by applying force through it or under subjecting pressure. So when you have the two fixed plates, it is not moving up at all, and you are storing a fluid for a longer period of time, it will be having some potential in it, right? So due to that potentiality, some amount of pressure will be developed. So due to this pressure, some amount of strain will be induced in the fluid, and due to the strain there will be some amount of the shear stress. Okay, so this is how it happens in case of static fluid. Similarly, the same thing has been done in for moving. So if by chance if you move one plate with respect to other, then the configuration what we get will be nothing but the sliding plate configuration. So what happens in both the cases, the gap is small in the direction of the field. So even though the plate is moving, yeah, fixed, the gap between the fibrils or the structures remains the same. So that thing will not vary. So that you have to understand. And the gap which is formed will be in the direction of the electric field. Suppose this is a direction in which the force has been applied, right? If it is for ER fluid, and you will apply the electric field. If it is for MR fluid, you will apply the magnetic field. So the gap which has been formed between the fibrils will be in the direction in which you apply the electric field, yeah, magnetic field. So that is being told over here. So the gap is in the direction of the field applied, and often 1 mm and of the order of millimeters in length is the direction of the flow or motion. So what do you understand by this? The gap in between the fibrils will be lesser than 1 millimeter of length, and this gap will be in the direction of the flow of fluid. So this is what you have to understand. Okay. So the closing spacing of the fluid is required in order to produce a field strong enough to activate the fluid. So this closing space, what is this closing space? You will be having a gap between the fibrils. So the closing space of the plate is required in order to produce a field strong enough to activate the fluid. So you need to have a closing phase. So when you subject an electrical field over here, so you'll be having the entire length of the fluid film. So you'll be having n number of fibrils. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So in between you'll be having the gaps. So the entire length of the fluid will be filled with this fibrils or the structure. Okay, so when it has been filled, when the spacing has been filled, so what happens is it helps to develop a strong enough electric field to activate the fluid. Means to say that when you have an uniform amount of electric field subjected throughout, it results in the formation of fibrils across each surface, and hence the viscosity of it will enhance right from the starting point to that of the end point. Due to high viscousness, the effect, the ER effect or the MR effect will be high in that particular smart fluid. Suppose if you don't apply a larger electric field, it can make the viscosity of the fluid high from this portion to this portion. So it might result in the formation of fibrils here, 1, 2, 3, and 4. But if the electric field is very less, it will not result in the formation of fibrils here, and as the viscosity here will not enhance. So the amount of ER effect what you need will not be achieved. If you want to achieve a good ER effect, yeah, MR effect, you should see that you will subject it to the required electrical field, yeah, magnetic field, so that the required viscousness is achieved, and as a result of viscousness, it helps you to provide an enhanced ER effect, yeah, MR effect, so that this fluid could be used as a smart fluid in any devices which are required. So this is about the post yield concepts. Okay, so after this, a simple analysis has to be done. So before going, yeah, that you have to see that the ER or MR fluid will be having an high value when you subject it to the required electrical field so that the fluid will be activated properly. Before deriving the mathematical model, you should see that the fluid is activated properly. It could be activated electrically or magnetically, but you should see that it is activated fully. If it is activated partially, then it can't give you an proper ER effect. Okay, so you have to see that once you have activated the fluid properly. So these, when the fluid is activated, then we call this as ER and MR effects. So when it is activated, you can assume that you have the formation of the fibrils in the direction of the electric field or magnetic field what you have applied. Okay, so it will be of a greater distance within the fluid if an advocate field can be generated. So that's what. So this fibrils could be at a longer distance throughout the fluid if an advocate amount of electrical field or magnetic field is applied. So then you can make the fluid active with full fibrils, high viscosity effect, and go for any application related to the smart fluid devices. Okay, so this is about the concept of post yield flow and devices, and later the derivation part has to be done. So here also the same researcher Wiss and Karslan has given a concept how to derive the basic mathematical equation for the post yield flow with respect to the device geometry. So that we will be doing in the next class. So today we just spoke about pre-yield stress, its response, and we derived a small equation for complex shear modulus, right? So, and what is meant by loss factor, right? And this loss factor will be lesser than 0.1 basically. But when the viscous is very high, then only the loss factor can be enhanced. So we dealt about the pre-yield response. Later we came about for post-yield response. We understood what all the concepts you have to keep in mind before deriving an mathematical equation. So currently I will stop at this stage. If you have any doubt, you are free to ask, or else I will take the attendance. Is it understanding? Any doubts? Are the things clear?
Yes, ma'am.
So, always you people tell yes. If any doubts, kindly let me know, because ultimately you are the one who will be going to write the examination. So tomorrow, yesterday's I'll be giving the attendance for the people who had submitted that assignment. I think many of you have submitted. I'll just see once again. So based on that, the assignment, the attendance will be given. And for today's class, I'll be taking the attendance now. So Danush,
Yes, ma'am.
Danush,
Yes, ma'am.
Mithun,
Yes, ma'am.
okay, Mohan Ambal,
Yes, ma'am.
Mohan Ambal, I think you are there.
Yes, ma'am.
Sandesh, yeah, Sandesh,
Yes, ma'am.
okay, Srinidhi, yeah,
Yes, ma'am.
Sukrut, I think he is absent. Sri Harsha,
Yes, ma'am.
okay. So everyone take care, have a nice day. I will just share you some links for the quiz, but instead of quiz, you have taken an assignment also yesterday. So that's fine. For in the next class, I'll be just giving you the quiz then. As you have given me an assignment yesterday itself, so that could be considered as a part of quiz as well. So no problem. And in the next class, I will share you the quiz link. Or else I will just ask you the questions directly in the next class. Please be prepared for it. So until then, take care and have a nice day. Bye bye.
Thank you, ma'am.
Yeah, bye.
Thank you,
Yeah,
ma'am.
yeah, thank you. Bye.